Today, we're looking at classical mechanics problems in Python. Specifically, we're going to look at different pendulums. So what is a pendulum? Well, the classic example is a heavy ball on a stick, and it goes back and forth and back and forth, right? But if you're thinking of different types of pendulums, the better way to think about it is a bead on a wire. So a regular pendulum would be bending a wire in a circle and letting the bead go back and forth on the wire in a circle. And then you can have different types of pendulums. You're not constrained by the stick anymore. You could bend it like a parabola and have the bead go back and forth and back and forth. An interesting problem is, how do you bend it such that the bead always takes the same amount of time to go back and forth no matter what height you start it from? That's known as a tautochrome, and we're going to look at it. And we're going to do everything in sympy so that no math has to be written on paper. And unfortunately, in order for me to use sympy, you're going to have to listen to this. DJ? Sup, dog? Is that a pencil I see? Math on paper so last century. Now we all simping for sympy. Got symbolic computation. Differentiate yourself out of any situation. Integrals, transforms, trig simplification. Satisfy your thirst with the pencil-free vacation. It's not Mathematica, but I'll take what I can get. Don't have myself a fortune to spend on that quite yet. Alright guys, I'm here in Python. Quite a few packages you can see today. So be sure to note that. Let's define our problem. We have a particle in space and it's confined to some one-dimensional path, meaning there's only 1 degree of freedom. The pendulum can rotate, the bead can go on the wire in a various way, and so we can parameterize everything in terms of theta, and I'll get to that a little later. This is typical. A few examples is a parabola where x equals theta and y is theta squared. So you can imagine a bead sliding on a parabola. The simple pendulum where x equals cos theta, y is sine theta. That's a bead sliding on a circular wire. And that's also the same as a pendulum rocking back and forth. And something we'll look at later, the tautochrome, is a pendulum or a way that you bend a wire such that no matter where you start the bead, it always takes the same amount of time to go back and forth. This isn't true for a pendulum. If you just have a pendulum and you let it swing back and forth, depending on where you start it, of course it'll take longer than others. And there's infinitely many possibilities you could do here. So once you solve this using the code here, you can plug in any path that you want. So important things to note, we have kinetic energy defined as T. This is obvious what it's defined as. Potential energy, well, we'll assume we're in a gravitational field for this problem. So V is mgy. The Lagrangian is L is T minus V. That's how the Lagrangian is defined. And then finally we have Lagrange's equation as such. And I made a point of saying we're going to do everything in Python, no paper, for this video. So let's start by defining our variables. And I'll show you how to do this in sympy. We know that everything's going to be a function of t, so I'm going to define something called t. There's going to be something with mass m, and there's a gravitational field g. And we need to define some symbols. And the way you do that in sympy is as such. And I need to import sympy. So now if I print this, I get a variable t. And I can go t plus m, and it'll return a nice looking LaTeX formula there. So I can manipulate these symbolically. I also need to define something called theta, which is this parameter here that x and y are a function of. And theta, as we know, is going to be a function of t in the end. So I need to make sure I specify that. So theta, and we give the little LaTeX formula here. And the class is going to be sympy.function. And we make a point of saying in the end, theta is going to be a function of t. So theta is equal to theta of t as such. So we have that defined. We're also going to define the derivative of theta and also the second derivative of theta. These will come up later. So theta underscore d will denote one derivative, and you can use the simp.derivative, simp.diff. This takes the derivative of theta with respect to t. And then we also have theta, the second derivative, which is the derivative of theta dot with respect to t. So I can print these, and I want to make sure that this is LaTeX. So here's, for example, d dt of theta. I put this little r here for raw string. Here's d theta dt, and here's the second derivative of theta with respect to t. So we're going to do all our math on the computer. Now we're going to define x and y, which are functions of theta. We're building up our problem. So x, y equals simp.symbols. And I'm going to put in x, y, and these themselves are functions as well. So we're going to make sure that we specify that. And x is equal to x of theta, and y is equal to y of theta. So you can see how things are being built up, right? X is a function of theta, and theta is a function of t. This is interesting. So now we need to define, we have x and y a function of theta. Now we're going to define the path. So we're going to define how they depend on theta. We know that they're functions of theta, but now we're going to give a specific function. So I'm going to start with the parabola because I think that's easiest. I'm just going to name it this so I can go back and change it later. And I'm going to say if path is equal to parabola. So that's x is equal to theta, and y is equal to theta squared. And now we're going to create, these are like functions in Numpy. So I'm going to show you what they do. Well, first of all, if I go like this, and I print x, then I get theta of t, and y is theta squared, as I've defined. Now I want to create Numpy functions that take in they take in theta, and they return x. And I can do this as follows. I call this, it's hard to spell, lambdafy, and I'm going to take theta and x. And I'm going to do the same for yf. And you'll note that if I plug in xf and I give a value of theta is equal to 2, I get 2. And yf should return 4 because it's quadratic. So now I not only have x and y, which are the symbolic symbols, I also have xf and yf, which are numerical functions. We're building up a repertoire here of things that we're going to use later. Next, we need to define t, v, and l. So we're slowly building up our classical mechanics problem. T is 1/2 times m times, and we have derivative of x with respect to t plus derivative of y with respect to t. So I can do that as such in sympy. So that's our kinetic energy, and I can print this, and you'll see that it automatically applies the chain rule. Because x is a function of theta and theta is a function of t, it'll return the chain rule version of this. Very, very useful with sympy. And I'm also going to do it with the potential y. It's a simpler one. So now I have t and I have v, right? And now I'm going to define L. That's our Lagrangian. So now we have our Lagrangian written in terms of theta and d theta dt. It always comes packaged together. Now we need to compute our Lagrange's equation, dl d theta minus d dt of dl d theta dot. And I can just do this directly using sympy methods. So simp.diff L theta, and then simp.diff. Now the outer derivative is going to be with respect to t, because we're taking the time derivative of now dl d theta dot. So L and then theta underscore d. And I'm going to call this LE for Lagrange's equation. I can print this. And now I have Lagrange's equation written here. And you'll note that this is equal to 0, right? That's Lagrange's equation. dl d theta minus d dt of dl d theta dot is equal to 0. So if I can first simplify this. This is always handy to do in sympy. You can call this .simplify method. And it will simplify Lagrange's equation as much as it can. It looks like it didn't do too much here, and that's fine. And what we want to do is we want to get a system of differential equations that we can solve. And so there's all this is equal to 0. Let's solve for the second derivative of theta with respect to time, because that will give us one differential equation. And then we'll solve for d theta dt as well. So let's solve for the second derivative. So I can go, this is the second derivative. So I plug in Lagrange's equation, and I want to solve for theta underscore double dot. And if I print this, this tells me that d squared theta dt squared is equal to this, right? So I have my equation. Now, here's a simple way, because we want to solve these ODEs in Python. Rather than solving a second order differential equation, we solve two first order differential equations. And the equations can be split up as follows. d theta dt is equal to omega, and d omega dt is equal to this second derivative. So we're solving for theta and omega. They're two variables in our differential equation. We have this as our first equation, and this is our second. And this whatever is returned is this down here. We've solved for this in Python. So we have both our ODEs. So I'm going to also write derive 1, which is just this derivative here, is just equal to d theta dt. That's our first derivative. So now I have derive 2. This is equal to this, and derive 1 is equal to d theta dt. So now we need to turn this into NumPy expressions. So I'll turn it into a function. Derive 2 underscore f. I'll call it like this. We're going to use this lambdafy function again. I'm going to plug in. And what does this take in? It takes in g, it takes in d theta dt, and it takes in theta. So g, theta, and theta dot. So I need to make sure I give all the arguments of the things that are in this expression. And I'm also going to, this is the function itself that I have to feed it as well. And I'll do the same thing for derive 1f. Only this only takes in theta dot, so I don't have to give a tuple here. I could just say takes in theta dot, and it returns what it takes in. It's a very simple function. The first thing, it just takes in itself and returns itself. So it's simple. So now I have this derive 2 function. And I can feed it values. So for example, I can plug in g is 2, theta is 2, and theta dot is 2. And it will return a value. Because now this is essentially just a regular Python function as opposed to a symbolic expression. So now I can set up my ODE that we'll solve in Python. I recommend you look at my earlier videos where I go over how to do this for simpler systems. So I'm going to create my system, as I always have to do in Python. And it takes in s and t. By the way, I'm defining s is equal to a vector, and that vector is d theta dt and d omega dt. And of course, in Python, we have to take in a function. It takes in, s is theta and omega. And it has to take in s itself and return the derivative, ds dt, which is d theta dt d omega dt. So it has to return a vector, and it returns derive 1f. So this is this right here is d theta dt. And what's it doing? Well, s1, that's omega. So we're saying d theta dt is equal to omega, right? That's very simple. We have two things. I take the derivative, d theta dt is equal to omega by definition. And the second one, derive 2 underscore f, and it takes in g, it takes in theta, which is s0, right? S0 is theta, and it takes in s1, which is omega, and it returns that derivative. So I give a comma here. And this is d omega dt. So now we have our system, and now we can solve our system. So I'm going to say we'll make go 20 times and we'll go 1,000 points. We use our G as 9.81 as well. And I'll call the ODE int function, which I've imported from SciPy up here. ODE int solves system of differential equations. So I can call ODE int. It takes in ds dt, which is our system of differential equations. We'll plug in some initial conditions. So for the parabola, I think it'll start at... what this says is it says theta is equal to... well, let's start at theta is equal to 2. So why not, right? Because our system S, so we're going to start at theta equals 2. That means that x is equal to 2 and y is equal to 4. So it starts at a point on that parabola. And it's going to have no omega to start, so it's starting from rest. And then we feed in our t is equal to t. And we can plot our answer. It's as simple as that. And remember the way that answer is returned. Answer will return these vectors. The first column is theta, and the second is omega. So in order to extract this column, I go answer.t. So I transpose it, and then I can take the first component, and that gives me theta as a function of time. So I can plot this, and you can see that it looks like a pendulum. It goes up and down and up and down and up and down. So the bead is going up and down on this wire that's bent like a parabola. Now I can solve for some other things if I want to. So I can call this answer 1, and we can solve for some different initial conditions. For example, start at 3. All right, so let's plot our solution. Take the transpose, 0. We plot t versus this, and then we can plot our second answer. Answer 1 and answer 2. And you'll see one of them theta starts at 3, one of them theta starts at 2, and it goes up and down like this. But here we're plotting theta. I'm more interested in what x and y look like as a function of time. So let's create an animation of x and y. So first I'm going to write a function that takes in theta and it returns xy. Theta. So return def get xy, takes in theta, and it's going to return xf of theta, yf of theta. Remember that we define these functions up here, xf and yf, so that we can have these numpy functions to play with later on. So here I have x of f of theta and y of theta. So it'll take in a theta and it returns x and y. So for example, I can take x, y of 2, and it should return 2 for x and y for 4, because we have a parabola. We can get our x and y points for our two answers. So get xy, we'll plug in answer 1, and we'll find it for another one. So now we have our x and y's as a function of theta. Now I say we animate this. So when we're going to use matplotlib, we need to define an animate function that takes in the frame number of the animation. And so let's set up our axis first. So we have create a figure. We'll make a grid on this figure. And let's start with some empty lines. So this will be used to plot our first solution, and this will be used to plot our second solution. These are just empty right now. There's nothing going on, and we'll add to them in the animate function. And let's set appropriate limits. So this gives us a reasonable limits, and let's create an animation. And our animate function, by the way, will just basically set the data here. So return, it will set this line data, so it just returns the coordinate x1 at position I, and y1 at position I. So this will plot our first solution, and this here will plot our second solution. Very simple. So we set our lines here, and in the animate function, it will actually set data, and so it'll move the point at a different place depending on the frame number. That's what I'm doing. I'm just indexing by I here. And we'll go animation dot imported. We'll give it a figure, our animate function. We'll go 1,000 frames. This interval, not important. I always set it to 50. And we'll save our animation. Save it as a gift, and I'll call it Pendulum. And I'll use pillow as my writer. And I'll save it at 50 frames per second. Now, there's a reason I'm saving it at 50 frames per second. That is because I went t is 0 to 20 with 1,000 points. That means that there's 50 times between 0 and 1. So if I go 50 frames per second, I take 50 times. And there's exactly 50 times from 0 to 1 seconds. So this animation is going to be in real time. I encourage you to think about that. 50 frames per second for this particular array. So I can run this cell. If everything is good, it should produce an animation of this. So we're going to see both beads. They're not going to collide into each other, obviously, because we've solved them separately. But you'll see them sliding back and forth on the parabola. All right, we're back. The animation is saved. Let's take a look at it. So here are our 2 points. They're not colliding with each other, but it's essentially a bead that's sliding back and forth on a pendulum. Now, the parabola is somewhat interesting of a pendulum, but there are more exciting things to look at. And I want to show you how versatile this code is. So we're done with that. I want to look at something more interesting. And we can do that by changing how x and y depend on theta here. Let's look at the tautochrone, the pendulum that always has the same period no matter where you start it from. And I used the wrong naming convention, so I'll call this taut, and I will call this parabola. And now all we need to do is restart and run all our code. Okay, so I've restarted the kernel, and we can run all the cells again. And as you can see, everything is going well. I changed the initial conditions here from 2 and 3 to np.pi/4 and np.pi/5, just because the system is parameterized differently. So I can run this cell. And you can see, sure enough, that they have the same period, even though they're starting from different points. And I'll prove it to you with this animation. I'm also going to change my x and y limit here from -1 to 16 to -1 to 4. Alright, so the animation is finished. We can take a look at it. And sure enough, even though these start at different starting positions, they oscillate at the same frequency. Now, this is true for the regular pendulum for small displacements, but for the regular pendulum, you get deviations in the period for large oscillations. For the tautochrone, it's always the same. But I've given you the formula, I've given you the code, so you can plug in any function you want here. You don't have to use the parabola or the tautochrone. Come up with whatever you want. Come up with whatever parameterization you want, run it, and see what happens. Anyways, I hope you've enjoyed this video. If you do, please like and please subscribe. I will be posting more interesting content in the future. Thank you.